Let's come to our next speaker, Klemens Hammerer from Institute of Theoretical Physics in Hanover.
Thank you, Dennis. Thanks to Dennis and all the organizers for getting me here, setting up this beautiful conference and list of talks. I'm going to talk about atom interferometers in weakly curved spacetimes using Bragg diffraction and Bloch oscillations, and I will explain those words. This is a collaboration with a group of Nasser Galul, a theory group in Hanover as well, and Domenico Giolini in Hanover, and Philip Schwartz, who was supposed to be here but now joins only online. Hi Philip, get well again. Michael Werner has done most of this work. He's also here and has a poster, so you can tease him with all kinds of questions in the afternoon or in the evening. And let me start by introducing my group a little bit. So, or let me start by first talking more about Nasser's group. Nasser is an expert in simulating atom interferometers. So this is a simulation of a real atom interferometer. What you see here is the density of atoms, flying off in a superposition here, getting reflected by a mirror and recombined here, and then they come out. So this is a Mach-Zehnder interferometer, and each of these operations is done with a pulse of light. That's an atom interferometer. Nasser is an expert, and his group an expert in simulating these things in all kinds of ways. Domenico Giolini, most of you will know, he's an expert in relativity, and I had the pleasure to collaborate with those two colleagues on this topic here. So my background is certainly not relativity. I'm working in theoretical quantum optics. Oh, the colors do not come out good here. In theoretical quantum optics, quantum information and metrology. So at this intersection here, and I'm a rather applied quantum theoretical physicist. I'm working on various setups like atomic clocks, atom interferometers, trapped ions, atomic ensembles, also cavity QD and waveguide QD, optomechanical systems, gravitational wave detectors, just to give you a bit of an overview. For example, in atomic clocks, to give a flavor of what we are doing there, we are trying to devise entangled quantum states and also entangled measurements to improve the precision and the stability ultimately of atomic clocks. In trapped ions, I have the pleasure to collaborate with colleagues at PTB, building ion clocks. So we investigate a couple of topics surrounding trapped ion clocks, like the mass effect and time dilation. I will come back to that point later on. Also, using quadrupole transitions, as you need to do for trapped ion quantum clocks, and using like quantum control schemes to make those transitions robust and good clock transitions. And connected to this mass effect and time dilation, I will come back on later, the temperature of ions in a trap are actually one of the main systematic effects of a trapped ion clock. So you need to know the temperature of an ion very well in order to know this systematic offset, and for that we need methods to do thermometry. So this is also something we did recently. But today I'm going to talk about atom interferometry actually, and with Nasser we are developing analytical and numerical tools to describe those things and make them efficient, make all those pulse operations, beam splitters and mirror pulses efficient. And with Domenico and Michael here we worked on this description of atom interferometers in weakly curved spacetime. Those two topics here, atom interferometers in weakly curved spacetime and the mass effect and time dilation, so you don't see a box which is appearing here, are built on work by Philip Schwartz, who was supposed to speak before me. So my talk was set up to build on what you know now from Philip. So now you don't know it, but you will learn it in the next talk because he will speak online still. Yeah, but I have to now explain a little bit on what he did. Yeah. So what he and Nico did was to develop a post-Newtonian Hamiltonian description of an atom in a weak gravitational field. Yeah, so what those two colleagues gave us is a beautiful quantum optical Hamiltonian, which looks in zeroth order of 1 over c squared like a normal quantum optical Hamiltonian for an atom in an electromagnetic and a gravitational field. Yeah, so you have center of mass motion as a degree of freedom, you have internal degrees of freedom of the atom as a degree of freedom. They are decoupled ideally, like in the basic course of quantum mechanics. When you treat a hydrogen atom, you start from a two-particle system, you go to center of mass and relative coordinates, and those two degrees of freedom decouple. And then you solve the Schrödinger equation for those 2 degrees of freedom separately. And in quantum optics, we have the dipole interaction with the electromagnetic field, and we put the Newton gravitational potential if we want to have it in a gravitational field. Yeah? So this is what we do non-relativistically. Nico and Philip worked out in a very rigorous way what happens in 1 over c squared in a curved spacetime, weakly curved spacetime, and in an external electromagnetic field. So we have the 1 over c squared corrections. And for example, for the internal degree of freedom, what you find is something like the hyperfine structure of an atom. And for the center of mass degree of freedom, you find all kinds of corrections, like for a point particle, like the p to the 4 term and all kinds of things. You will see it later on. Yeah? And then, interestingly, also center of mass and internal degrees of freedom are coupled in 1 over c squared. Yeah? And this is due to the mass effect. I will come back to that later on. So there will be a Hamiltonian, which gives us a rigorous description of the center of mass degree of freedom of an atom and an internal degree of freedom of an atom. And this you need to describe something like an atom interferometer or an ion in a trap to describe rigorously the relativistic corrections in an ion clock. Okay, so I will build on what Philip is going to explain to you in the next talk, and I apply it in that context here. Let me talk a little bit about atom interferometers. Yeah? Atom interferometers are devices where we take a cloud of atoms, maybe 1,000 or so, or 10,000 at most of atoms, maybe in a Bose-Einstein condensate. We prepare a nice wave function, and using light pulses, so that should show a standing wave field here, one can devise light-matter interactions such that atoms are driven in superpositions going off with different momenta for a while. Then they are reflected, recombined, interfere here in a final beam splitter pulse, and then we detect the output boards. And what one can measure from measuring those populations is essentially the phase which atoms see or pick up along those 2 different paths. And this phase will in particular scale with the enclosed spacetime area A. So if you want to have a very sensitive interferometer, the rule of the game is to make this area large. Yeah? And that means we have to transfer a lot of momentum. This is the momentum imparted on atoms here in this beam splitter operation. And we have to have a long flight time. And that means a huge interferometer. That makes our interferometer sensitive, and it can be sensitive to a lot of different things. Atomic recoil, from which we effectively can measure the fine structure constant. We can measure gravity. If gravity is imprinting the phase here on those 2 paths in different height in the gravitational field. We can measure the gravitational constant by bringing test masses in there. We can test the equivalence principle, space-time curvature, gravitational waves even. We can do quantum clock experiments. I will come back to that later, and maybe also physics beyond the standard model. And all of this is very nicely reviewed also in this CERN workshop summary, first authored here by Sven Abend, who many of you will also know. Yeah? As a matter of fact, there are 2 applications of atom interferometers with the highest sensitivity so far. This is the measurement of the fine structure constant in Paris and in Berkeley. And here the measurements of the gravitational Aharonov-Bohm effect and space-time curvature across the atomic wave function. This is the Kasevich experiment. All of those most sensitive large momentum transfer interferometers achieving a really large space-time area here are using what is called Bragg diffraction and Bloch oscillations. So what is that? Bragg diffraction means that we use standing wave light fields and diffract atoms of that optical grating to generate a light a beam splitter or a mirror pulse. On the other hand, Bloch oscillations means that after splitting up the atoms using such a Bragg diffraction, one loads the atoms in an optical lattice and then accelerates the lattice, and in this way imparts a lot of additional momentum to the atoms. So these are two workhorses in high sensitivity atom interferometry. And in our investigation, we looked at those on atom interferometers which are built on those two tools here, because currently they are the tools achieving the highest sensitivity. In these cases, the atoms remain in the same internal state. So this is all elastic scattering from the point of view of the atoms. We do not change internal states. And this is good for sensitivity, because if you bring in additional states, you go from a ground state to an excited state, then you have different electronic states, and there are all kinds of systematic effects associated to that. So it's not an accident that, like the most sensitive experiments, like the fine structure measurements, use this elastic scattering. You get rid of this electronic degree of freedom. That doesn't mean you cannot do useful experiments with that. There will be future generations of atom interferometers exploiting also the possibility to transfer atoms to a different state. And I will come back to that when I mention quantum clock experiments. Good. This is just to explain a little bit what I mean by Bragg diffraction and Bloch oscillations. These are really tools to impart momentum transfer or bring atoms into large superpositions in momentum, and then later on also in space, of course. What we were looking at in the context of these atom interferometers using this Bragg diffraction and Bloch oscillations were questions like, what are the fundamental losses and phases involved, what are favorable working points, what strategies can we have to avoid losses or suppress phases. So what is the technical side of such an interferometer? And I refer you to these recent publications here on some nice ideas we had on these questions here. But what I'm going to talk about in this talk is, what are the leading order relativistic phases of such an interferometer? And this is what Michael was working on for a long time, and which is something to be published now and accepted at PRD recently. We're, of course, not the first to ask this question. What are the relativistic phases in an atom interferometer? And I will start with this very early and pioneering work by Dimopoulos, Graham, Hogan, and Kasevich, who worked out exactly that question in great detail for a Mach-Zehnder interferometer. There are two papers from 2007, 2008, and I think these are still very, very influential papers on this topic of atom interferometry in curved spacetime. They looked at this particular topology, a Mach-Zehnder interferometer, and this dashed line and the solid line here denote atoms in different internal states. So this is something we didn't look at yet, and would correspond to quantum clock experiments. But if you imagine this is the same internal states, then this falls into the category of interferometers we wanted to describe. In those papers, they worked that out. What is the phase, the relative phase between the two trajectories of the two components of the wave function in great detail? And what they started with is a Schwarzschild spacetime in ppn expansion. So you see this post-Newtonian parameters beta and gamma, which are 1 in GR, and the rest is the normal metric. And from that matrix, by solving the classical trajectories along the two paths, one can work out the action along the two paths, and that will give the propagation phase. So actually it will be the relative phase between those two paths. Then there will be what is called a separation phase. That's a maybe rather technical thing, which is connected to the fact that maybe those two trajectories do not ideally close in the end. And a third component in the relative phase between the two arms here will be the kick phase, which comes from the light-matter interaction in the mirrors and the pulses. So they work this out in a very systematic way, and the result is this. Yeah? So it's a really nasty table of phases with scalings, with the transferred momentum k and some power of the flight time here, and then there is g and gradients of g and second gradients of g, and you know, that was it essentially. And then there are these beta and gamma ppn parameters, and they give you know numbers for a specific setup they had in mind in these years. Yeah. But of course now time changed. We can now think of much you know, more complicated interferometers which are not Mach-Zehners. We can add Bloch oscillations. We can think of much larger interferometers. So it would be good to, you know, be able to reproduce that and put in different numbers. And it's not so easy if you read those papers. And the reason is that they did that in an algebraic way, but you know, with a Mathematica code which is not available. So it's hardly reproducible. But it would be good to reproduce that, because again, it would be nice to be able to discuss that for different interferometer geometries, and to start also a derivation from a really quantum optical Hamiltonian, in the sense of what I explained before, provided by Nico and Philip. And we would also like to do that in a sort of automatic way, in order not to do this by hand here. And this is what we tackled, starting from Philip's and Nico's work. So we took their Hamiltonian, and I will show you this Hamiltonian in a second, which also starts from this ppn Schwarzschild matrix, and then we started doing that calculation. And the first thing we stumbled over is, when you do that, you find that suddenly everything depends on the gravitational potential here at the position of your experiment. So you have the phi naught, you know, phi on the surface of Earth, floating around your equations everywhere, and somehow also seemingly making a contribution to your phase, which is weird, because you should not be able to measure phi naught. Yeah? And the reason for that was that we were much too naive, to take Philip and Nico's Hamiltonian and apply it to this atom interferometer, because what they are using here are asymptotically flat coordinates. Yeah? They are Minkowski far away from Earth. But if we describe an experiment on the surface of Earth, where we measure lengths and time with respect to ideally an atomic clock sitting next to it, this atomic clock will be redshifted and so on. Yeah, so we should use adapted coordinates. If we don't, we can of course do the calculation in the non-adapted coordinates, in these asymptotically flat coordinates, but then we cannot apply the naive Born rule to our calculations. We have to correct with the metric whatever we calculate from our quantized non-relativistic or perturbed relativistic description. And this we don't want to think about these things. Yeah, we want to do a non-relativistic quantum optical calculation, and I don't want to discuss the metric. Yeah, so I have to adapt the coordinates. Yeah, of course you can do it differently, but for us it's easier to adapt the coordinates. And if we do that, then the metric changes a little bit, and instead of the gravitational potential phi, we get always this shifted phi, which is the phi minus the phi naught. So on the spot on our point of reference, which will be the position of our clock, which we use to define time and length, this is 0. So all the corrections beyond c squared are 0, and here we have a 1, so we have a Minkowski metric, which is good. And the phi naught still appears, funnily, in that metric, but it is, this term is absent in GR, because beta is 1, which makes a lot of sense. So now we do everything in that coordinates, and for us that was sort of an important point to make sense of what comes now. So Phillips and Nikos Hamiltonian consists on a bunch of terms. This is the center of mass term, the internal term, the coupling, the relativistic coupling of COM and internal, and the atom light coupling, because we think of the atom in an external electromagnetic field, which we need to apply to generate these beam splitter and mirror pulses. So let's look briefly at those terms. The center of mass position is what you would expect from a free particle in a gravitational field, and then you have the usual corrections coming. 5 minutes? Yeah, okay. The usual corrections here. And this will be the most important term here, because we use it to calculate the propagation and the separation phase. This gives the phase along the trajectories of the interferometer. The internal degree of freedom will be, what we solve for the hydrogen orbitals, but there will be the hyperfine structure, but this is sort of given. We know how to treat that. This is the center of mass internal coupling. There will be in particular a correction depending on the internal Hamiltonian and the effective mass of the particle. This is the mass defect term. There are also additional terms. I jump over that now. The physics encoded in that coupling is, at the heart of the so-called redshift debate, and at the heart of many papers coming from the Schleich group from Ulm, Albert Ruhrer and Fabio Di Pumpo, and so on. In our case, where we do not assume that the internal state changes, this term is not contributing to the phase. Finally, the atom light coupling will have the usual dipole and the Röntgen term, and it will be responsible for the kick phase from the laser atom interaction. So from that Hamiltonian, we essentially solve the Schrödinger equation. Now, in the usual approximation for atom interferometers, we do that for different geometries. This is a symmetric Ramsey-Borde interferometer, symmetric double diffraction, asymmetric Ramsey-Borde. So they differ in the paths which atoms take in that space-time regime here. And the main challenge is to calculate this propagation phase. So the action along the upper path minus the lower path. And we do that by expanding the potential up to third order. So we take the gravity and gravity gradient and the gradient of the gradient, and we apply a one-dimensional theory. That is again this center of mass Hamiltonian. What we have to do now in order to determine the action along those paths is to solve the Euler-Lagrange equations, which is a tedious thing. And that can be done systematically, and that is, I think, the big achievement Michael managed to do here by a good bookkeeping, because there are a lot of small parameters in this problem. There are initial conditions, there is a Doppler shift, there are gravity terms, there is a recoil term, and if you look at that for something like a 10-meter baseline interferometer, they're all small. So one has to do the right bookkeeping with all of these small parameters, and then you're able to, in an automatized way, work out the phases. And this is what we find. And this is now the corresponding table corresponding to Dimopoulos. But now we can do that for this or that geometry and many more geometries you may think of. So this is the one interferometer, this is the other interferometer, this is the third interferometer. And with it QR, you find a code where you can calculate these things by the push of a button. Algebraically, in Python, not in Mathematica. Good. There are non-relativistic terms. This is a PPN term. There are gravity gradient terms and Doppler effect terms. We can also plot them, and then you see that the non-relativistic terms here, these are the dominant ones, and then there is a big gap, and this is the next order of these small parameters. And those are terms which depend on gravity here. In each of those three geometries, this is a 10-meter baseline interferometer, and here are the same things for 100-meter baseline interferometers, where these relativistic phases are on the radian scale. Now, 100 meters sounds crazy, but there are a lot of devices being built around the world. This is the 10-meter VLBI device in Hanover, but and there are many more large interferometer facilities being built up. I put here the impressive picture of Saiga, which has a 240-meter tower here underground being built up at the moment. Good. There is also this piece on trapped ions. I jump over that. You can ask me if you like. And with that, I stop and I advertise Michael's poster, where you can find all details on these tables. Good. Thank you.
Thank you very much. And are there questions? Christian?
You said that these gravity effects, they are very smaller than the non-relativistic effects. Is enhancing the length the only way how you can enhance this gravity effects, or is there any other way to optimize the experiments to see the gravitational effects?
So in effect, you would always run the experiment in a way where you would somehow get rid of these dominant orders of magnitude dominant non-relativistic terms, and one can do that by doing some differential measurements, running two interferometers in parallel at different heights or so, and then subtract it in such a way that you get rid of these strong terms. So this would be something which is required. Otherwise, you would not see them. And then, on top of that, making the interferometer large is certainly the most important handle in order to increase that from the from milliradian scale here to the radian scale.
Would that go into space or something?
I mean, flight times could, I suppose, be also very good there. Yeah. I mean, there are plans to go to space also with atom interferometers. Yeah.
Okay, so there's another question.
Yeah, one short question. Can you maybe shortly talk about this clock interferometer using different internal states? Yeah.
Yes. So exactly. So in here you don't see any clock interferometer, and no, this is the other way around. So a clock interferometer would exploit the fact that in the center of mass, in this coupling, in the Hamiltonian, there is this coupling between center of mass and internal. And it looks actually like this, and Philip will talk about it, but one can think of those terms, in particular, those first terms, by the mass, the center of mass, depending on the internal state. So if we correct the rest mass, center of mass rest mass, by the internal energy of the atom, or h bar omega Eg over c squared, and we expand this p squared over 2m with this tiny correction, we exactly get that coupling which comes out from the calculation of Philip and Nico. And that also gives phases. Now, if atoms fly with different internal states, they have effectively different masses, which have different, kinetic phase and also different gravitational phase. And this is exploited in a clock experiment. And that can be a very, sizable and important phase also. And I should add, I always, oops, now I switched that off, but maybe that's also the right point. I should pay tribute, but Philip will do that in the next talk, I suppose, that Klaus Lemmerzahl was, of course, pioneering in working out these relativistic corrections for quantum optical Hamiltonians.
So are there any questions from the YouTube stream, or no? All right, so if there are not any urgent questions, so maybe we shift the questions to the coffee break. But now we have to rebuild a bit because we have a talk by Trust that is going to be on Zoom. Let's thank Klemens again for. All right.